So it's really a pleasure to present with you today some materials about a project that Chris and I and Allie Baczynski somehow got ourselves involved in over the last 6 months or so, and we'll be participating in over the next 3 years. I'm going to do a couple of things today. I want to just review a little bit about the asteroid and the mission itself. There's a lot more to it than just the little bit that we're doing. And then I'll focus in on more of the geochemistry that we're doing and some of the questions we're trying to answer, and some of the tools that make the Penn State team really unique within the very large array of scientists who are studying this or potentially studying the samples when they come back. And so I'll say a little bit about our contributions. So see, I think I have to do this. Maybe I'll do this. That works. There we go. Okay, so Bennu is small. Small is relative, I suppose, but in terms of bodies in space, it's pretty small. So it's not much bigger than the Empire State Building. And, towers a little bit over the Eiffel Tower, if you have the opportunity to see that. So it's a small entity in space that has captured the interests of NASA and the European Space Association for a variety of reasons, but in particular because they think it carries signatures of the earliest solar system and in particular, some of the building blocks that become foundational for the origin of life on our planet. So one of the things that was a surprise to me when I got involved in this project was, well, first of all, how many asteroids there are out there. And I mean, it kind of looks like, when my kids are adolescents, it kind of looks like their bedrooms, right? It's like there's a lot of stuff on the floor, right? So there's just an enormous number of asteroids. And one of the things that's really interesting about Bennu is that it's actually really close to Earth. It's part of this population of near-Earth asteroids. That most of the asteroids are outside of Mars, but there's this population sort of within the inner solar system. And these are the ones that are thought to be a potential threat to our own well-being. And in fact, it wasn't just last year that we went and sent a mission and that it threw itself at the asteroid and tried to knock it off course as an experiment to see if we can do that, right? So this is the same category of asteroids that are of concern in that regard. And Bennu is one of them. So that's one of the motivators for the mission, is just to learn more about asteroids that are proximal to Earth and in our neighborhood. Where is it today? Well, here it is. You can see Bennu is down here in the lower part of the screen. The Earth is the blue dot there. So the orbit is actually fairly close to the Earth's orbit. And you can see associated with that, the little dot next to it I put on there, that's the OSIRIS mission on its way back from having sampled material already on asteroid Bennu. So it's closely tracking it, and it's due to arrive back on Earth in September of this year. So I just made this today. You can go on NASA and the website, and they'll let you play around with images of the solar system, and you can create images of where things are as we speak, or at any period in time that you're interested in. It's pretty terrific outreach tool. Well, so as I mentioned, Bennu is proximal to the planet in a relative sense, and it could hit the Earth. But you don't need to take out insurance just yet. Because it's not likely to hit anytime soon. But if you'll notice, so this diagram is a pretty interesting one. It's a distance to Earth in Earth radii. So here's 100 radii, and it gets pretty down below that in the year 2135. So there is a significant threat to the Earth, but you guys don't need to worry too much about it today. But that is part of this category of asteroids that kind of in their orbits sort of swing near the Earth at some point, potentially could interact with us in a, what do they say, non-nominal way, right? NASA speak. But that also makes it easier to access and go get samples from and bring it back. So that's a quality that's a positive in that way as well. So why is Bennu so close? Most of the asteroids are outside the rocky planets. There's this population that's migrated in. It's thought that the reason for that is related to the Yarkovsky effect, which is something I really don't know a lot about, but I've been trying to read up on it in my journey as a member of the Bennu science team or the OSIRIS science team. And so the way this works is that the sun is heating the body and it's rotating as it's orbiting the sun as well. And if this part gets warm and then rotates that way, then there's some IR radiation that kicks off of it. And it effectively acts like a brake. And it slows the movement of the body. And in that way, because its velocity is slowing, then its orbit sharpens. The radius of the orbit is reduced. And so that's bringing it slowly closer to the center of the solar system. And if it was rotating in the other direction, so this is rotating this way, but if it was rotating the other way, it would actually serve to accelerate, be a little rocket boost of IR radiation in, opposite of the direction of travel, and that would actually increase its velocity and widen its orbit. And so one of the big justifications for the mission is because these bodies are near the Earth, they are a potential hazard. We really don't understand this effect very well, and we want to understand it better because it is maybe one of the things that's bringing them closer to Earth and dictating where they go, as moving forward. And one of the properties that's really important here is their ability to radiate IR energy. So that's a black body radiation feature. And so getting to know the surface of the material and some of the properties of it from that perspective is a big motivator for this whole mission as well. So that's the Yarkovsky effect. My slide. So here's a picture of Bennu, a mosaic of pictures put together by the OSIRIS-REx team. You can see that it's rubbly. It's got a lot of chunks of stuff on it. It is, as I said, about the size of about 500 meters. It's very small microgravities. It's not like Earth. It doesn't have the kind of pull because of the small mass. And it's got this boulder-dominated terrain. OSIRIS, the spacecraft, spent about 2 years studying and taking images and doing spectroscopy and all kinds of cool things on this body out near Earth. And then eventually it collected a sample and is now bringing it back. And so last April, just almost a year ago, they put out a call for other scientists who wanted to join the science team. And so we put together, Chris and I and Allie put together a proposal last spring. And then we learned in August that we were selected to be part of the team. So it's all still a little new to all of us. We're trying to get up to speed on it. So that's OSIRIS, or I'm sorry, that's Bennu. And it's one of the properties that makes it really of interest to us and to many people on the science team is that it's really dark. And this is some of the reflectance information about its albedo. It's a very dark body, and that actually is influential in its radiation of infrared radiation associated with the Yarkovsky effect, but it also means it probably has carbon in it, and a fair amount of carbon. And so for an organic geochemist like me, that makes me kind of rub my hands together and lick my lips with excitement at the idea of looking at some of the organic molecules that might be brought back. Now, what I'd like to emphasize for you is that everything about the mission to Bennu has been full of surprises. And I mentioned that it's a microgravity environment and it's kind of rubbly. And this is an image from the mission. And you can see those little light sprinkles coming off of the asteroid. You can see it on both slides. Those are bits of rock that are spewing out. So the idea is that something in space maybe hits the asteroid and then it releases particles as a result of that. And so it's got material leaving the surface continuously. Some of that stuff just goes off to space, and they've been modeling it, trying to track these things, and a fair amount of it actually returns back to the surface of the asteroid. This was not something they were planning to study or looking for, but discovered as part of the mission. And so here's an example. That's that same image I showed you previously. Here's the model where they're tracking these little particles of rock that have come off of the asteroid, many of which return back to it through that little microgravity, but some don't. And it's even calculated that some have probably made their way to Earth. And so this would be one origin for meteorites that we get on Earth today. It's these little shedding of particles out in space. From our perspective, we actually wrote in our proposal that we wanted to study weathering of organics on the space or on the asteroid surface. But what this is telling us is actually that surface is regenerating itself on pretty quick timescales. And so what we thought might be a few billion years old might actually only be a few 100,000 years old in terms of the age of the exposed surface of the asteroid. So that changes a little bit how we think about the chemistry we might encounter when it comes back to Earth. Okay, so this is a video from NASA. This was made before the sampling. And you can see that that's the sampling device going down to the surface. This is all just a cartoon image. And watch this, boom. All right, so you see that? It lands with a thump, right? That's what they thought they were going to get when they did the sampling. And then there'd be a little bit of scatter, but not too much. So that's not at all what happened. So here you can see it. This is all, again, the cartoon or the model cartoon, taking that sample container, putting it in its little egg carton. It's going to hold it, bring it back home. Boop, there it goes. So that's the video of what. So the important thing about that video is that the sampler landed with a thud on the surface, and it had in it sort of gas jets that would sort of excavate the surface, and then it had these filtery battens that would collect the rock particles and bring it back. All of that part still happened, but the thud did not. So let me show you that. So this is, well, so one of the first things they ran into is they thought, if you remember in that video I showed you, it was pretty smooth. So one of the first problems they encountered is that it actually is incredibly rocky. And these are not small rocks, some are 50 meters. And it's really uneven terrain. So you can see this image is sort of looking like, where are we going to take our sample? It's not smooth. And when it's not smooth, that means you have a safety for the spacecraft concern that comes up. You want to not have interactions with the surface in a way that are unpredictable. And so they backed off on their sampling plan and said, all right, we got to think about this. And so they came up with they looked through their survey of the images of the asteroid and came up with 4 candidate sample sites, did some studies on all 4 sites to try and come up with the candidate, or the one site that might be the least risky to the goals of the mission and the spacecraft itself. You can see they named them all after birds. I'm not sure why birds or what the origin of that is, but they ended up picking Nightingale as the sampling locality. And it's still pretty rocky. I mean, there's a huge rock right there, right? So but nonetheless, they decided this is the one they were going to go for. And so here is the video of the actual sampling. Remember that analog that I made of the teenager's bedroom? Well, this is like that times 100. So as this device goes down, instead of a thump, it actually gets a shower of particles come up, amazing shower particles. And as it's going down, they realize it's not hitting anything. And so the thrusters came on, and that's the only reason we had a spacecraft survive this whole encounter, is that it was already programmed to turn on its thrusters because it's too far away to give real-time commands. So they can't do that. But it was pre-programmed to turn on its thrusters and back away from the asteroid after about 6 seconds, and it did do that, but otherwise it probably would have kept going. So that's kind of cool. This sampling event, here it is. This is from a side camera, so you can see the shadow of the sampler coming down to the surface, and then it's going to show you the sort of the spew of material that comes out from that. Look at that. Isn't that crazy? So that's all material that's liberated just from the encounter of that sampling ring on the surface of the asteroid. And then it's backing away. You can see that as the thrusters got it out of there. So it made this huge debris plume, and it went down much deeper than they expected below the original surface of the asteroid. You can see it backing away here. None of this was what they were expecting. And so here's a video that's recreated the experience of sampling Bennu. You can see it coming down. It's very rocky. This is the Nightingale site. They've created this movie based on the data. And then look, it just keeps going. And then it's still going down. There's debris everywhere. The thrusters come on. And that's the reason we have a spacecraft to return to the Earth, because of that pre-programmed thruster fire. So they're going to spin us around a little bit in this video. They've got a great visual team for this mission. All of this stuff is available on the NASA website. If you'd like to take a look at it, I can point you towards it. So you see it, here it is. So it's got a lot of, it's sort of stop motion there. Now it's going to come up and out from where it went after the material. Yeah. So human beings are pretty good at leaving a mess. And here is yet another example of that. As you can see, there's a lot of debris around where it's sampled, and it reorganized or moved material during that sampling process. And that's been, they reprogrammed the mission again after the sampling and said, oh, we got to go back and look and see what we did. And so they did more imaging of the site after it had been sampled. Oh yeah, this is, yeah, so sorry, I forgot about this slide. Yeah, so what they now think is happening in this asteroid is that it's a very microgravity environment. There's no cohesion amongst the various particles that make it up. And basically the whole thing is one big ball pit. Okay, and so this is, has anybody been to a ball pit? Yeah, and right? Yeah, they're a little gross actually, but nonetheless, they're really fun for kids. And there's no cohesion with those particles. And basically that's what this asteroid body is. So, and then when they went back and let's see, yeah, the crate they made, so the crater was created. That's the surface of it. And so now they've done this little video to show you where it was depressed. And then they actually show you where the thruster marks. So the thrusters themselves actually left a mark in the surface of the asteroid as well. So the whole thing excavated a fairly large volume of material, about 12 cubic meters of material was excavated to create this crater. It's about a meter, 1.1 meter, sorry, its depth is about 0.7 of a meter, not quite a full meter down. And the upshot is that the material is nearly cohesionless. There's nothing really holding this together except slight microgravity, and it's very granular. So we don't know what's going to come back in the sample container, but my guess is it's going to be a lot of fine material based on these images. So you can see there's the imaging. There's some pretty large rocks that kind of got displaced by this process. So it was a pretty theatrical moment in NASA's sampling history. Okay, I think there it is. This is actual video of the little container of sample being put on the spacecraft and the lid being locked down for it to come back to Earth. So the sample, when they brought it up, I got a question in earlier before the public lecture about their leaking. When they actually pulled the sample container off the surface, there was so much debris that there was a debris stream coming off of it. And so it suggested to NASA that the container is actually pretty full. They had originally planned to figure out the mass of sample by rotating the spacecraft and getting the momentum, right? But they were so worried about material leaking out that they didn't want to do that. So the only measurement of momentum that they have is just the arm itself coming up and putting it onto the deck of the spacecraft itself, that little bit of an arc in there. And so the estimate's not great of how much they got, but from the sample quantity perspective, people are pretty optimistic that it's more than meets the goal of the mission. So they think they've got 250 plus or minus 100 grams on deck coming back to Earth. The mission is defined as success if it gets 60 grams, right? So even with that error bar, they're still working in a range that's comfortably above the success of the mission. And so that 60 grams is the baseline case. And then anything more than that, they call that an overguide. And so there's actually, when we wrote the proposal, we had to write a proposal for the baseline because you never know what you're really going to get. But then we also had to write a second part of our proposal. It's like, well, if there's more, then we will do all these other amazing things with it. And so we don't know till it lands on Earth, but there's a lot of hope that we will be in that overguide situation and have fairly generous access to samples as a result of that. We at Penn State, if we're in an overguide situation, our total allotment will be about 2 grams, which is about the amount of a pack of sugar, which is actually enormous, because the entire return for the Hayabusa mission to asteroid Ryugu, which was done by the Japanese Space Agency, that whole thing was 5 grams, whole return. So we're really working in a different realm of potential sample materials with this particular mission. There's a lot of work today trying to figure out how to take in, working through plans to take in that material and then distribute it amongst the science team, which is over 500 people, as I understand it. And we think there's a fair amount of dust that's actually going to come back, as well as they're hoping large chunks, which would be nice. And then, oh yeah, this says the Earth return will be late September in this year. So we're hoping it'll be a smooth landing. So they say the landing will be in proving grounds in Utah, in the United States. And the plan is to have 2 wheeled vehicles, so Jeeps, and then 2 helicopters to go and pick that up. It's a proving ground, so that means there's potentially unexploded ordnances from military operations on there. So none of the scientists are allowed to go on that pickup effort. Okay. So one of the things that we know about Bennu that was actually known a fair amount before they went after it on this mission is that it is hydrated, means it's had water as part of its history, and it's carbon rich. So that is one of the reasons that from Chris and I's perspective that is of great interest to us. It's got these potential building blocks of compounds that might be prebiotic. The imaging, when they were circling around the asteroid and taking pictures of it and doing spectroscopy on it, it's pretty clear there's actually veins of carbonate mineral in addition to really dark areas that are organic rich. So it's not just carbon, there's like a lot of carbon, and there's both reduced and oxidized or hydrated carbon on this surface. The organics have been studied using spectroscopy. So you can see this number here, the H to C ratio. I'll show you a little bit more data about that. That tells us something about the nature of the organics, not a lot, but it tells us a little bit and based on sort of analogy with meteorites and these kinds of chemical properties, there's thought to be sort of hundreds to maybe 10,000 parts per billion amino acids. And so there's a lot of interest, of course, in amino acids as a prebiotic compound. And so that's one of the targets here. The Goddard team, you heard from Jose Aponte a few weeks ago, there's actually a lot of interest in the amino acids because it's a water altered system. There's some thought that water alteration leads to an L excess in amino acids. And so that's a hypothesis that the Goddard space team or organic team is really all about, and they're really excited to test that with these samples. So, but space weathering can destroy that. So that's that last bullet point there. And as I said, the whole thing is sort of resurfacing itself. So to me, it's really unclear what the space weathering environment is like for these organics altogether. So we will find out when it comes home, I guess. So here's some of the data on Bennu. This is based on the sort of spectroscopy done while the spacecraft was orbiting the asteroid. And it's just these measurements of infrared spectroscopy. And so there's a range of values. And then that's the blue and the red in each of these graphs. And then it's just overlaid with properties of meteorites that are on Earth that have been characterized. And so they're trying to use these meteorites to say, okay, if that's the value on a meteorite, and this is the value we get on our asteroid, then maybe it has the same chemical properties. It's a pretty sort of simplistic way to do your geochemistry, but it's a pretty good way to do it based on what we're trying to do here. So first of all, the hydrocarbon to carbon ratio is about 1/2. That's pretty much what you get with sort of complex polycyclic aromatic hydrocarbons. So it seems it's not very hydrogen rich. The organic content, the total carbon content, is probably somewhere between about, the red is sort of the the average, and then the blue is the organic rich or the darker portions of it. So it's somewhere between sort of 1 and 2% organic carbon. That's actually fairly high abundance. And then this is sort of comparison of both bulk organics and hydrogen to carbon ratios to sort of say that it looks like a carbonaceous meteorite. So they're based on these spectroscopy data. They're we're all kind of rubbing our hands together with excitement about this organic rich, possibly water altered, but fairly interesting sample that's going to come back to us. And so I made this comparison of Bennu to carbonaceous chondrites, or meteorites. So I just want to bring this up because not everybody may be familiar with these this categorization. So meteorites, when meteorites fall on the Earth, scientists run over and try and get it into a clean space as quickly as possible. A lot of our meteorites are actually collected in Antarctica because they fall in this massive continent of snow, and you can collect them there. In fact, the way the ice moves and actually upwells, it brings older falls to the surface in certain localities. So there's a lot of interest in collection of meteorites on Antarctica, but they fall elsewhere. And in fact, they fall all the time. And they're categorized based on sort of their basic properties of iron, stony, or stony irons, cleverly named. And then either they don't or they do have chondrites, which are little blebs. These are thought to be more primitive. And then if they have a lot of carbon in them, they're carbonaceous. So carbonaceous chondrites is sort of this main class of meteorites where the organic studies tend to be focused. And then there's a whole slew of them. And let's see. I think the Murchison, Murchison is right in here. And so these on the left are more organic rich and less altered. The ones on the right are more altered through their journey through space. The naming of these things was a sort of a mystery to me until I've just recently learned that they are named based on the name of the first meteorite that has its characteristic. So these are all C for being carbonaceous, but then the letters are actually based on the name of some meteorite that was characterized that has that characteristic. So they're named by minerals. They're categorized by minerals and then by organics second. And so carbonaceous chondrites are thought to be kind of representative of these carbon-rich asteroid sources. And so organics on meteorites come to Earth today or sometime in the near past, and they represent sort of a long journey of the organics that are carried on them from before there was even a solar system. So the interstellar cloud that collapsed to form our solar system had organics in it. And so there may be some residues or materials that carry the signal of that interstellar material. Then it formed the solar nebula and then eventually into the solar system itself about 4.5 billion years ago. In that early solar system, there was some parent body that maybe broke up and formed asteroid bodies that we know today. And maybe some of that breaking up process led to the release of meteorites that end up on Earth. So that's the idea, is that the Bennu is sort of sampling this time period in the early part of the formation of the solar system, and it carries then organics in it that maybe reflect some of the interstellar material as well as material processed in the early history of the solar system. And what we've since learned is that all along, it's actually resurfacing itself. So there's some processing that's happening along the way. Okay, and then from an organic perspective, when we think about that transition from that pre-solar nebula to planetary processes, there's kind of an increasing molecular complexity that goes along with that. So interstellar medium and interstellar molecular clouds are characterized by organics and ices, but not very many bonds. So 1 or 2 bonds in the gaseous phase of interstellar media. And then as you move into kind of concentrations of this material, you maybe get a few more bonds, but it's only really when you get into the early history of the solar system and the formation of planetesimals that you begin to, it's thought that there'd be more complex organics. So whatever's on Bennu represents probably a sampling of material kind of that has journeyed through this entire sort of process of increasing complexity. Okay, So that's my background on Bennu. I don't know how I'm doing on time. Oh, okay. So I have a few slides to share with you about the project here at Penn State and why, what makes us unique in the science team and what we're trying to do and some of the questions we're trying to answer with our techniques. So yeah, so I already introduced the people. So just so you know, we have myself and Allie Baczynski, who's over here, and Chris House. And then we're actually looking for a postdoc to help us with this as well. So if you know anybody who's excited and wants to do some mass spectrometry, send them my way. So the four of us, postdoc to be hired, are going to be working with trying to answer a set of hypotheses about the origin and history of the organics on this asteroid. And these are all hypotheses that actually the mission put together early on. And then when we wrote our proposal, we said, well, we can help you with this part of the hypothesis, or we can help you with that hypothesis. And so all of ours are really interested in the origins and the alteration history of the organics. SOM is soluble organic matter, so that's small molecules. And then IOM is the insoluble organic matter. It's the big kind of cross-linked stuff. That's probably the bulk of it. And we want to use molecules and their isotope signatures to trace these sources and alterations. And so what we're interested in just describing it. So one of the things, Bennu keeps giving us these surprises. So really one of the first job is just to characterize what is in those samples and what does it look like, how much is of different forms, and what characteristics does it have. So just describing the material is job one. And then from that, we can begin to, think about what happened before it was made into an asteroid. So the asteroid itself was probably the products of the breakup of a planetesimal, and that recoalesced to form this ball pit of an asteroid. So what can it tell us about that planetesimal? That's one question. And then how has that material changed through time? It's experienced surface processing throughout its history. And then what are the properties that are reflected in the organics for these different materials? And space weathering is sort of embedded in a lot of these kinds of questions that the mission was originally asking. And so everybody is kind of resetting what they're thinking about and how to address questions of space weathering, given the dynamic nature of the planet, the asteroid surface. So I work with carbon isotopes primarily. I do work with other elements as well, but we're really interested in using the isotopes of carbon embedded in molecules and in organic materials as a signature of where they came from and how they've been altered through time. And so there is a fair amount known about carbon isotopes in space in our solar system today. There's a really nice, and I forgot to put his name on here, Broadly is a review article. It just came out. It's really nice on the volatiles that are on Earth and where they came from. And as part of that, there's a nice summary diagram of the carbon isotopes in space materials. And this is not differentiating organics versus inorganics. It's just sort of space materials. And you can see that the Earth is really tucked in there with all the other carbonaceous chondrites. It's sort of similar to other materials. Jupiter is more depleted, and it's halfway between carbon in grainy material and in gaseous material, CO gaseous material. And it's just recently, it's been shown that Jupiter value is also very similar to the sun. So the sun has a value that's similar to that. And so it's if material in the asteroid has sort of this combination of grainy material and gaseous material from the formation of the solar system, we might see sort of very large variations of signals of that of those sources in our samples. Oh, I didn't mean to do that. Sorry. Just need to settle down here. There we go. Okay. So, and in fact, this is some recent work from the legacy of the Genesis mission. Do people know about the Genesis mission at all? So Genesis, okay, thank you. I love a nodder in the audience. So the Genesis mission was a mission that was sent out, and it sort of orbited around and collected solar wind, and then it brought it back to Earth. Do you know what happened to its landing? It was not a nominal landing. So it crashed at about 180 miles per hour on the Earth, on Earth. And so it was kind of a mess. And so they had to go and pick out the pieces, but they were able, with painstaking effort, to pull out materials that had been embedded in their sampling device safely, and were able to get isotope measurements of the sun by sampling the solar wind, which was the goal of that work. So the solar wind oxygen isotope is shown here. It's about -60 in both both 17O and 18O. And that actually really nicely ties on this sort of meteorite, this mixing line that it characterizes many of the attributes of the solar system. And then they just recently published the carbon isotope value for the protosun as captured in the solar winds as kind of this mix of material that looks like the planets and then this depleted gas in the early formation of the solar system, which is really interesting to me because it says that if the organics in Bennu have this mix of stuff, it might be sort of values that are close to what we have on Earth and then really low values. Okay, and that would be a kind of a neat sort of detective tool to pull those possibilities apart. And these are not small differences. This 100 per mil or so. It's theatrical from Earth perspective. So Earth is, you can see the blue dot. Carbon on Earth is about -5. And that's the value that's canonically used to represent carbon in the mantle. Actually, Penn State is responsible for a lot of those measurements through the work of Peter Dinas. Peter Dinas measured diamonds collected out of kimberlite deposits that represented carbon from the mantle. And he personally is responsible for most of the measurements that represent that number. So there's a really, really Penn State proud component there. So there's that. I said there's this sort of rocky value, rocky planet value, and then this gaseous CO value. But there's actually this other part of the story, which is all the stuff outside our solar system. And that actually turns out to be, here's sort of estimates. It's hard to make these measurements, but it's thought that actually stuff outside our solar system is going to be more enriched in 13C than anything in our solar system. So there's this, and this is due to a variety of factors, but this is probably related to self-shielding reactions. These are based on measurements using radio astronomy, and the ratio here is 12/13, which is the inverse of how most Earth-based geochemists do it. And so anything below us would be enriched in 13. And so our solar system is here, and then everything else from measurements in the interstellar media are well below us, so they're much enriched in 13C. And in fact, signatures of that do show up in meteoritic organics. So that is suggesting that there's interstellar material that ends up in these early organics from the solar system's very beginnings. And this is a really exciting example of that. This, sorry, her face is blinded by the temperature name, but this is Elle Shimiak, who did a really beautiful study of organic isotopes carried in alanine. And you see this is the alanine structure here. There's 1, 2, and 3. And she made measurements of each of these by using some mass spectrometry techniques that I'll talk about in just a minute. And the values that she measured are here. Here's -40, -35, plus 140. So that middle carbon has this really theatrically enriched signature, which is that, and she is interpreting that as that interstellar signal coming in and being part of the organics. So within the molecular forms, there's vestiges of interstellar media through its isotope signatures. And this is not a subtle signal. It's 120 per mil, 130 per mil positive relative to 0. So these are strong signals and very, very exciting possibilities for unpacking the origins of materials or of carbon in organics. And she compared, this is her previous data, which I just highlighted by coloring those circles in the previous diagram. And then she's comparing this to a whole bunch of other data that are at the whole molecule value. So not the individual sites, but the whole molecule. And we see a large range, but as you see, they kind of go up towards these elevated values in the smaller form, suggesting that there's a core to those molecules that is carrying that interstellar signature. So it's a really kind of new dimension of information about the origins of these molecules. And we can make those measurements here at Penn State. And that's what we're hoping to do. Okay, so one of my favorite tools, I think every girl should have a mass spectrometer. And in fact, I think mass spectrometers are like shoes, and you need one for every occasion, right? So I have a closet full of shoes. I also have a closet full of mass spectrometers. Actually, it's not a closet, it's a large lab come see us. We're in the basement of Dyke. We'd be happy to give you a tour. Mass spectrometry all is based on the Lorentz force law, where charged particles move in either a magnetic field or an electrostatic field. And we take advantage of how charged particles, if they're negatively charged, they're attracted to a positive charge. They're positive charge are attracted to a negative charge. We take advantage of that. Or if they are moving in a magnetic field, their movement gets pushed by their interaction with the magnetic field. So we take advantage of these two properties in all forms of mass spectrometry. I was recently preparing this slide for my isotope geochemistry class, and I was kind of thinking about, well, you know, there's actually an example of this process that's become very popular in this debate about whether we should all get rid of our gas cooktops or not. And that's to replace them with electric stoves. But actually, we don't want to replace them with electric stoves. We want to replace them with induction cooktops, because induction cooktops work with the same Lorentz forces to generate, it makes field lines that interact with your pot, and those field lines actually get the electrons excited inside your pot, and that creates heat right in the pot itself. So there's no transfer of heat from the flame or from an electric burner into your pot. That's the inefficient part of cooking and energy consumption. So if you can actually create the heat in the pot itself, you save a fair amount of carbon in the process. And so induction cooktops use the Lorentz force principles, which I think is pretty cool. So it's sort of marrying some things that I like, which are mass spectrometers and cooking. So anyway, and you can see here's an example of the cooktop itself doesn't get hot. Those are ice cubes right next to a boiling pot. It's only in the pot itself that creates the heat, because it's an iron-containing pot that interacts with the field lines of the magnetic force created by an alternating current right below it. Who knew science could be so useful? Okay, so anyway, so now you not only need, you know, mass spectrometers like shoes, but you maybe need them like cooktops. I don't know. I digress. So you heard from Jose Aponte a couple of weeks ago about the work that they're doing at Goddard, and I really just have this slide up to show what it's sort of a summary of the things he talked about. When a material comes in, or when they're working, these are for meteorites, but when the material comes in, they crush it, they extract it, they either use solvents or water, and then they use various kinds of mass spectrometry to characterize the organics in those samples, including measuring isotopes of the individual compounds in that lower right corner. We do all of that too, but we can do these measurements, particularly these isotope measurements, with orders of magnitude less material than they can. So we're partnering with them to let them do this part, and then we'll take those samples and we can look at the trace components in them and maybe make measurements of the isotopes that they are not able to otherwise. So this is the nut of the core of our proposal that was funded. We're going to do 4 kinds of measurements on the Bennu samples when they hopefully return more successfully than the Genesis mission. And that is that we'll have isotope measurements of solid material and isotopes, of soluble material and isotopes of the insoluble material. So the bulk material, the complex organics that you can't extract simply, we'll look at them this way. And then those compounds, the molecules that you can extract, we'll look at them with these techniques. And so the work that they do at Goddard will feed into this analytical channel for us. And then we're going to be actually partnering with folks at the Carnegie Institute of Science in Washington, D.C., who does a lot of this kind of work. And so we'll be kind of coordinating with them. So I'm going to just explain briefly each of these techniques. And we're basically going from left to right, from big, actually, Allie, to eensy teensy. But big is relative here. How are we doing? Yeah. No, that's not what I want to do. Yeah, okay. So the first technique is what we call nano-EA IRMS, which means nanoscale elemental analysis, isotope ratio, mass spectrometry. And what that means is that we burn the carbon, turn it into CO2, do the same for nitrogen, turning it into N2, and we can measure with high precision the isotope abundances of those phases that are produced. And Allie Baczynski has worked very hard on making this possible. And did I not put your citation on here? Just recently came out with a nice description of this trapping-free method that she developed that allows us to work with particles. This is the lower diagram. Sort of depending on the amount of carbon in those samples, we can make measurements below 0.5 millimeter with relatively good precision, 0.1 to 5 per mil precision, which is more than enough to differentiate, the interstellar versus the solar system organic signatures. And likewise, actually, nitrogen is kind of the drama queen of isotopes when it comes to these things. I haven't really talked about that much, but we can make similar scale measurements of nitrogen isotopes in there, and again, begin to differentiate sort of the sources of nitrogen from interstellar versus planetary processing. Well, that's one. This is Chris, and really, Chris, I should put you on the spot, but I won't do that to you. So Chris is one of the world's experts. Yeah, he's very understated about this, but he's actually one of the world's experts in this technique of spotting with a ion beam, a surface of material, sputtering off components of it, and then measuring the isotopes of that material. It's secondary ion mass spectrometry, and he's been working on this throughout most of his career, and one of the really hallmarks of his work is the ability to really standardize the material rigorously. And so his spot sizes are about 15 microns. So if material comes back in the spaceship that's not completely ground up powder, but there's some chunks of rock, he can actually do spatially resolved isotope measurements and look at the heterogeneity of the components and their potential sort of signatures of origin. So that's two. Those are the solid phase materials. The liquid phase materials we can measure with two kinds of mass spectrometry. This is picomolar scale compound specific isotope analyses, or PICO CSIA. Again, Allie Baczynski developed this in our group, and this allows us to make measurements on peaks that are less than 0.5 second wide, and we can make high precision isotope measurements on about 100 picograms of combusted compound, which is pretty small amount. And so she's worked really hard to give us great peak shape, and it comes with like really wonderful separations. We can get a suite of compounds separated from each other and make high precision measurements of those. These are some biomarkers from the Precambrian that we just submitted the manuscript for, but she also was working with aromatic structures, which is what we think is more likely to be present on the asteroid sample. So that's 3. And then 4 is high resolution, high accuracy mass spectrometry that uses an Orbitrap analyzer. So it's a sort of new generation of instruments that are really powerful and sort of separating very closely similar masses. So you can separate isotopes from each other with this technique. I could talk a lot about this, but I won't do that to you. But if you're interested, come find me and we'll be happy to tell you more about these techniques. They were invented. Actually, the patent is just over 20 years ago. It was patented by an employee of Thermo, which is a mass spectrometry company, and they've become really, really important and widely used in proteomic studies. So when you want to sort of unpack all the amino acids in a protein to get something about its function and also origins, these are the tools of choice for that. We're not looking at proteins, we're looking at small molecules. And because we're working with small molecules, we can actually resolve individual isotope or isotopologues from each other with this technique. The actual meat of the instrument is not very big. These are Orbitrap analyzers here. That's a nickel, and that's a euro coin for scale. So they're pretty small, and they're actively being developed for flight in NASA missions and European missions. And the Penn State team has really benefited from some close collaborations with John Eiler's group at Caltech, and I spent part of my sabbatical there in 2019 and 20 before the COVID, whatever brought me home. And so we've enjoyed a really nice collaboration and benefit from their expertise with a variety of elements of this. So we have one of these instruments here at Penn State, and we're using it to separate isotopologue. So I just have a little bit of information about what I mean by that. This is alanine. So that's that same molecule that Al Shimiak with the purple hair analyzed. And you can see there's carbon in various forms. There's a nitrogen and some oxygens and hydrogens. And if it's substituted with a deuterium versus a carbon-13, that's an added of 1 neutron and 1 nominal mass unit. But the actual mass is slightly different, and it's different in the 3rd decimal place. So it's about 0.003 difference in mass. And so we need a resolving power of about 30,000 to separate those isotopologues, deuterium versus 13C. Our instrument can go up to about operationally it can go to close to 250,000. We tend to operate at about 150,000 mass separation power. So we have a lot of horsepower to do this separation and do this analysis. A lot of separation power. So that's 4. So those are the 4 instruments that we're using, that we proposed. I'd just like to highlight some recent work from Hao Ji, who's in the back of the room there, who's been working with our instrument here at Penn State to look at the isotopologues of vanillin. And I like this choice because it is has some aromatic character to it. So it's kind of analogous to some of the things we expect to see with Bennu. And so the way it works is that you can actually measure the different peaks from that carry the different isotopes in the fragments of the molecule. Instead of turning it all into CO2 or all into N2, we can actually leave it intact, kind of break it up, and then look at the chunks and look at the isotopes in the chunks and then put it back together mathematically to get an isotope signature. So that's what he's doing here. And his work here has been focused on a variety of things, but you'll notice that each of these fragments has an oxygen in them. And so he's been actually trying to make an isotope measurement of the 3 oxygens in this compound. And so I just want to tip my hat to Allie yet again. The pico CSIA and the nano EA IRMS techniques, she worked really hard to get peaks as narrow as possible, half a second wide, really, really tiny bandwidth on those peaks. And then I said to her, well, you know, we need to actually measure these molecules longer, not shorter. And so we needed to expand the peaks. So we actually developed a trapping system. And this is a figure that Yuki Sato, who's here, developed, and that's your figure, right? Is that, yeah, thank you. And you worked hard on sort of figuring out how to make this work, along with Hao and others. And we actually trap a peak that we're interested in it. We kind of let it diffuse in a space and then re-release it so that we get actually, instead of half a second, we get 10 minutes of measuring time. So we can get really nice precision on the rare isotopes in these molecules. And just to wrap up here with the last bit, here's Hao's work on vanillin. This, I should say, this is in collaboration with Max Lloyd as well, who provided these materials. And so he's made these measurements that kind of track those 3 different red balls, which are the different oxygen atoms, using the isotopologues of the different fragment ions. And this is my last slide that I'll of this particular material. And these are the isotope measurements that do they still hold up? Yes, okay, because it seems to change as we're learning to do this better and better. But nonetheless, here are the 3 different oxygen groups. And these are commercial samples, standards that he bought, and then these are some natural materials. And what I just want to call to your attention is that there's about a 300 per mil range in these oxygen isotope values for materials here on Earth. So when we go into space, it's really an exciting kind of frontier area, even on Earth, to understand what is locked in these isotopologues. And then to take that into space is really just an exciting possibility and privilege in my mind. Okay, the last thing, I'll just close with a sort of recap of what the Penn State team proposed and was selected to do. And it's based on these sort of innovations in our ways of making isotope measurements and the longstanding capabilities of our team members. So there's the sample. We can measure tiny, tiny 0.5 millimeter size grains or smaller to get carbon, nitrogen, and sulfur isotopes using nano EA. We can spot in 10 to 20 micron sizes if there's a material that's sufficient for that to get diversity in the patterns spatially. We can look at molecular averages for different structures, for carbon in particular, and then we can look at within those molecules for patterns that might tell us something about their origins, both out in the interstellar media versus the planetary history or the solar system history of the materials.